Hello! Thank you for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with people who watch my videos online. Life is far too short, the world is much too big, to waste the opportunity to connect with each other. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist, because that does encourage me to keep making them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones for you. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats, so I'm just going over basic concepts. And I will be doing so in a very slow, deliberate manner. Not only do I want you to understand what's going on, but also why and how to apply it. So all that being said, let's go ahead and get started. So this video is the next in our series on hypothesis formulation and eventually hypothesis testing. So in the videos leading up to this one, we talked about the concept of type 1 and type 2 errors. And that can seem like a very confusing topic, and for many students it is. So in this video, what I'm going to try to do is make it visual. I'm going to show you some graphs so you can visualize what type 1 and type 2 errors are, and actually sort of what's going on behind the scenes when we talk about type 1 and type 2 errors. So let's go ahead and dive right in. So remember that we have the standard normal curve, and you should probably know that by now. The area under the curve equals 1, which is the same thing as the probability under the curve is equal to 1. So if we split the curve into sections, everything to the left of the midpoint would be 50%, everything to the right would be the other 50%, so you kind of see how that works. Now this is the sampling distribution of means. So the curve we're looking at here is actually a distribution of many sample means. So we call that X bar. So if we go into a population, maybe it has 1 million people in it or 1 million things, and we take many samples over and over again of the same size, we could put those samples into their own distribution and it would look something like this. So that's called the sampling distribution, just to remind you. Now, of course, we're interested in putting that concept into the idea of hypothesis formulation and hypothesis testing. So in the previous videos, we talked about what the null hypothesis is and the alternative hypothesis. So in this video, I'm going to show them in a little bit different way because it's going to prepare us for hypothesis testing in the next video. So you can see here we have mu and mu sub 0. Now mu is the actual mean of the population under analysis. And mu sub 0 is the hypothesized mean of the population under analysis. So what we're talking about here is, does the actual mean align with the hypothesized mean? And of course, we will test that question using sample means and confidence intervals when we do hypothesis testing proper in the next video. We have a hypothesized mean that's given to us in our problem. Then we're going to go out and take a sample of that population, and we're going to test whether or not that sample is from a population that aligns with our hypothesized population. That's all we're doing. Now, if that seems sort of a circular way of talking about things, I wouldn't be surprised. But again, the next couple of videos are meant to actually show you visually what we're talking about. So let's go ahead and take a look at the first one. So let's say we have a hypothesized distribution here. So here we have mu sub 0. And again, that's our hypothesized mean. That's what we're going to be given in the problem. Now we can put that in a confidence interval. And again, we talked about those in previous videos, so I won't go back into that. And we can set up boundaries. Now we're going to choose an alpha of 0.05. That's called our significance level, or our type 1 error rate, which we'll talk about here in a bit. But basically what we're saying is that 95% of all the sample means we take are hypothesized to be in this blue region. Now remember our null and alternative hypothesis. So our null says if we take a sample, and we take many samples, and we have a sampling distribution, that distribution of samples should basically be right on top of this distribution. That's why the equal sign is there. Now the alternative says that that's not the case. So if we take samples and we have a sampling distribution, that sampling distribution will be either off to the side to the left, below, or off to the side to the right as compared to this hypothesized distribution. So let's look at how this would actually work. So let's say we take our first sample, and that's x bar sub 1 here. So that's our first sample mean. And as you can see, it's right there in the middle. Now, how would this affect how we interpret our null and alternative hypothesis? Well, in this case, we would fail to reject the null hypothesis. Why would we reject the null hypothesis? Because that sample mean is right smack in the middle of our hypothesized mean. So therefore, it seems like the null hypothesis is supported. It holds, quote, true. So we would not reject it. We would fail to reject the null hypothesis. So let's say we take another sample, and it ends up right there. Well, it's a little bit higher than sample 1, but it's still within that blue region. So, again, we would fail to reject the null hypothesis. So maybe we take another sample, and it ends up here. Again, we would fail to reject the null hypothesis because it's in that region. Sample 4, same story. Now, let's say we come to sample 5, and look where that is. Well, that is outside of our interval. And what would we do then? In that case, we would reject the null hypothesis. So that's so far outside of our hypothesized mean that we would reject the null hypothesis that this came from the same population as our hypothesized population. There must be a difference between the two. Now let's say we take another sample, sample 6. Well, again, we would fail to reject that null hypothesis. And sample 7, we would fail to reject that one. So what do we make of all these samples? Well, what we can say is probably that our actual population mean is about right where that green mu is. So it's pretty close to the hypothesized mean, but you can see it's kind of the middle of all the green regions, all of the green samples in this graphic. So if we took a sample and it was by chance, like sample 5, we would incorrectly reject the null hypothesis. So you can think of that sample as kind of the one oddball out of all the samples we could take. And again, remember, statistics is never perfect. So there's always that chance we're going to take the oddball sample that is either well below or well above the hypothesized mean. And in that case, we would end up rejecting the null hypothesis when we should not. And that is type 1 error. So that is classic type 1 error. We reject the null hypothesis because by chance we get a sample that is too far away from the hypothesized population mean. Therefore, we reject the null, but we do it incorrectly. Because we would take many more samples and we would fail to reject the null. And that's always a risk we take when we're doing sampling and testing hypotheses. Now remember, alpha is called the level of significance. And this is our tolerance for making a type 1 error. So in this case, our alpha is 0.05. So what we're saying is that if we did this process 100 times, we would expect about 5 of these sample means to be outside of that blue region. And that is how we interpret graphically type 1 error. Now, what about type 2 error? So repeat the same process. So here is our hypothesized population mean, and we still have the same things we did before. So now we take a sample 1, and now it's outside of the hypothesized population mean. So in this case, we would reject the null hypothesis, because obviously that's outside the boundary. Our null hypothesis says it should be within that region, and therefore we would reject it. So let's take another sample. Again, we would reject the null hypothesis. Let's do another one. Again, we would reject the null hypothesis. Take another sample. Now what about this one? Notice that this is within our region. So what will we do? We would fail to reject the null hypothesis, because our null hypothesis says that this sample comes from a population that is the same or aligns with our hypothesized population. So according to this sample, that is the case. So we look up at our null, it says they're equal, so therefore we would fail to reject it. Take another sample. Well, again, that one's outside, so we would reject the null. Again, we would reject the null. And again, we would reject the null. Now, what sense can we make of this? Well, it would appear that our actual mean, or actual population mean, is outside of that region. So you can see the green mu symbol there sort of is in the middle of all those green arrows, that green region. So it would appear that those samples are coming from a population that's different, statistically different, than the hypothesized population, except for sample 4. So if we took a sample and it was by chance like sample 4, we would incorrectly accept the null hypothesis or fail to reject the null hypothesis. And that is type 2 error. It's the case when we should have rejected the null, but we did not. Because again, we got an oddball sample that in this case is sort of the higher end of the actual population, and therefore it put it into that region, and we failed to reject the null hypothesis when we should have. Now this is called beta, and it is the probability of committing a type 2 error. Now unfortunately, it's not as easy to compute as alpha is. It varies depending on things like sample size and alpha level and things like that. So we're not going to go into calculating beta, at least in this one, but just keep in mind that alpha, our significance level, is the probability of committing type 1 error, and beta is the probability of committing type 2 error. Let's talk about the two-tailed test rejection region. So everything we have right now is the same as we had before. Our null is the same and the alternative is the same, and our alpha or significance level is the same. So we'll go ahead and put our curve here, and what do we notice? Well, our hypothesized population mean is there in the middle, which we expect. Now we call this blue area the non-rejection region. And when we go into hypothesis testing, that will have a very concrete meaning. But for now, just keep in mind that we call it the non-rejection region. On the ends, in the tails, we call these the rejection region. Now realize that this is called the two-tailed test rejection region. Well, why is it called that? If you look at our null hypothesis, it states that the actual population mean should equal the hypothesized population mean. The alternative, therefore, is that it does not. But it could be either below or it could be above if the alternative is the one that's supported. So we have to take into account both possibilities. That's why it is two-tailed, because we don't know which side it may fall on if the alternative is the hypothesis we're going to support based on our analysis. Now, in this case, the tails combine to account for an alpha of 0.05. Now that 0.05 or 5% is evenly divided among both tails. So in the bottom tail, we have alpha divided by 2, which is 0.025 or 2.5%. In the upper tail, we have alpha over 2 or 2.5%. So we're just splitting that alpha among both tails. Now the point at where we go from the non-rejection region over to the rejection region is called the critical value. It's sort of the threshold between those two regions. So it sort of sets boundaries on whether or not a mean is within the non-rejection region or the rejection region. So what we're saying is that if the null hypothesis is correct, then alpha times 100%, that's a fancy way of saying 95%, of the sample means should be in this non-rejection region, the blue in the middle. Now the critical value is determined by alpha and if we are using the z or the t distribution. Now we will not go into that here in this video, but we will be talking about it in future videos when we actually do hypothesis tests. And we'll talk about when to use the z, the standard normal curve, or when to use the t. So what are we really asking in this process? Did our sample come from the same population we assume is underlying the null hypothesis? That's what we're asking. If so, then we expect our sample means to be inside the critical region, 90%, 95%, or 99% of the time, depending on what we choose for our alpha. Now remember, whatever our alpha is we choose. So for an alpha of 0.1 or 0.10, we would have 90% in the blue there. We'll show that here in a second. For an alpha of 0.05, we would have 95% in the middle. For an alpha of 0.01, we'd have 99% in the middle. So just keep in mind that what we're asking is, did our sample come from the same population we assume is underlying the null hypothesis, or the hypothesized population mean? So let's take a look at a few curves here. Now if you notice, we're going to change the alpha level for each one. So in this first curve, we have alpha is 0.10. Now look at the blue region there in the middle. Now how do you compare that to the next curve? So look at our alpha of 0.05. Now look at the blue region in that curve. What do you notice? Well, the blue region in the middle, the non-rejection region, went outward. It got wider. And this should make sense. In the first case, we're saying 90% of our sample means should be in that non-rejection region. In the second curve, we're saying 95% of our sample means should be in that non-rejection region. Well, to get 95% of them in that region, the region's going to have to be wider. Now look at the alpha of 0.01. Now the non-rejection region is actually further out than the 0.05. So our critical values on the ends go even further outward. So what we're saying is that 99% of our sample means should be in that non-rejection region. So in order to attain that, we're going to have to widen our non-rejection region. We're going to have to widen our critical values. So what we're saying there is, as alpha decreases, as it shows in these graphs, so 0.1, 0.05, and 0.01, as alpha decreases, so does the chance of type 1 error. So as alpha decreases, the chance of type 1 error also decreases. The critical value to reject the null hypothesis moves outward, thus capturing more sample means. So it's kind of like moving the goalposts on a football pitch outward. The wider they are, the more kicks on average are going to go in. So to capture more of the sample means, the area widens out, and that's as our alpha decreases. Now, what does that mean for type 1 error? Now that error decreases is because since the area is wider, more means are going to fit into that. So therefore, our null hypothesis will be supported more of the time, and we are less likely to reject it incorrectly. Now, let's say we have a sample mean over here on our first curve. How would we interpret the null and alternative hypothesis? Well, here we would reject the null hypothesis because it's outside of our non-rejection region. It's in our rejection region in the lower tail. Now, what about this mean? Well, notice it's in the exact same place. The location of the mean has not changed. It's in the exact same place. But what did change? The alpha changed. So that means our critical values went outward. So how would we interpret the mean under this alpha level? Well, it's close, but we would still reject the null hypothesis. It's just outside that region. So it's in the rejection region, just on the other side of the critical value. Just barely, but it is. Now, same mean, same place. Now what will we do in terms of our hypothesis? Well, in this case, we would fail to reject the null hypothesis. Because see, it fell within our non-rejection region. So you can see that by decreasing the alpha, we were able to include that mean. But again, the question is, should we have? So in the first two cases, we rejected the null hypothesis. And in the third case, we failed to reject the null hypothesis. But the question always is, should we have? Now notice again, the mean didn't change location, only the alpha levels did. Now, however, the move outward of the critical values may also capture a mean from a different population that's kind of off to the side, like we showed in those previous two videos. We would fail to reject the null hypothesis when indeed we should reject it. Thus, the chance of type 2 error increases as alpha decreases. So there is an inverse relationship between alpha and beta, given the same sample size. So as we decrease the chance of type 1 error, we increase the chance of type 2 error. And that's the delicate balance. That's why we always sort of have to keep in mind the chance that we may incorrectly reject a null hypothesis or fail to reject a null hypothesis. So let's talk about one-tailed tests very quickly. So basically everything here is the same. Now our hypothesis changed a little bit. So you can see that our null says mu is greater than or equal to mu sub 0, and our alternative is that mu is less than mu sub 0. Same alpha level, alpha of 0.05. Let's go ahead and draw a curve. Now, what do we notice about how the curve relates to our hypotheses? So notice our null says that the actual population is greater than or equal to the hypothesized population. So if we look down here, we can see that we have our hypothesized mean there in the middle. And if our null is supported, then our mean that we find should be in this blue region all the way up to and including the entire right side. It's a directional hypothesis. Now, if we reject the null, then it's going to be down in that rejection region over there on the left-hand side. Now, in this case, all of the alpha is in one tail. Remember, in the two-tailed test, we split the alpha between both tails. So we had 0.025 in the left tail and 0.025 in the right tail, or the upper tail. Now, because this is a directional hypothesis, we put all of the alpha in one tail or the other, in this case, the lower tail. Now, in a one-tailed hypothesis test, all the alpha is in one tail or the other, depending on our alternative hypothesis. Now, the trick to this is that the alternative hypothesis points direction to the tail where the critical value and rejection regions are. Not just a quick trick, but hopefully you sort of understand it conceptually from the actual hypothesis. So let's say we have a mean that falls over here. Well, that's obviously in the rejection region, So we would reject our null hypothesis up there in the right. Remember, our null says that mu should be greater than or equal to mu sub 0, our hypothesized population mean. Well, this sample mean is way down below. It's in our rejection region. Therefore, we would reject the null hypothesis and then proceed onto the alternative. Now, the alternative says that mu is less than mu sub 0. And that appears to be the case based on this sample down here in the lower left. So we're saying that this sample mean is from a population with a mean less than our hypothesized population mean. So what we are positing is that this sample is from some other population with a mean less than our hypothesized population mean. Now what about this sample over here? Well, we would fail to reject the null hypothesis. Because remember, our null says that this actual population mean is greater than or equal to the hypothesized population mean. Well, this sample seems to support that. So we would not reject that null hypothesis. So it appears that this mean is from a population with a mean greater than or equal to the hypothesized population mean. So again, because our sample is in that non-rejection region, we would fail to reject the null hypothesis. So let's go ahead and quickly look at the other one-tailed test, and that's the upper region. So in this case, our hypotheses are switched. So the null says that our actual population data we're working with has a mean that is less than or equal to the hypothesized population mean. The alternative says that the population mean of the data we're working with is greater than the hypothesized population mean. And again, we're using an alpha of 0.05. So we go ahead and put this in our curve. And again, it looks just like the lower tail, but it's flipped on the other side. So again, we have our hypothesized population mean there in the middle. And then our alpha is all in the right side, all in the upper tail. So in a one-tailed test, we already went over this, all the alpha is in the one tail or the other, in this case the upper tail. So again, the trick is that the alternative points to the tail where the critical value and rejection region are. So you can see that the greater than sign in the alternative points to the right. So that is where our alpha is. So let's say we get a mean, a sample mean, and it falls here on the left-hand side. How would that affect our hypotheses? Well, in this case, we would fail to reject the null hypothesis. This is why we call this the non-rejection region. Because if the sample mean falls here, we failed to reject the null hypothesis. So according to our null hypothesis, the population mean of the data we're working with is less than or equal to the hypothesized population mean given in our problem. Now, what if this sample falls here? Well, in this case, we would reject the null hypothesis. And that should make sense. This sample seems to be coming from another population that has a mean that's higher than that in our hypothesized population mean. Now remember, we could also be committing an error. So it just depends. Now it also means we could be committing a type 1 error. That's always the risk. But based on what we see here, this mean appears to be beyond our hypothesized population mean. So just a few causes of type 1 and type 2 errors. I went over these in the previous video, but I'll just go over them really quickly in this one as well. So remember that when selecting samples, we are always subject to the laws of chance. We may, by random chance alone, select a sample that is not representative of the population. We may select a sample of underfilled or overfilled water bottles. That was the example in our previous video. We may select a sample of very small or very large farms. Again, that's from an example in our previous video. Or just in general, the sample is in the far out tails of the sampling distribution. Because remember, the sampling distribution is a distribution of many, many, many samples. Now, some of those samples are going to be out in the very far tails of that sampling distribution. And just by chance, we could get one of those when we make our sample, just by chance. Now, our sampling techniques may be flawed. That's always a possibility. The assumptions in our null hypothesis may be flawed. So if we make a null hypothesis based on some hypothesized population mean, and that hypothesis is wrong, or the number in that is wrong, then that's really going to mess up our hypothesis test. But that could happen, and it does happen. So in the previous video, we talked about USDA data in terms of the farm size. So what if the USDA went out and did something wrong in the research, and therefore they come up with a hypothesized population mean that we're going to use? But we go out and do our analysis, and our number is drastically different. So, did they make a mistake in their sampling, or did we? Is their hypothesis about the farm size correct, or is ours? So you can see that the assumption underlying that null hypothesis may be flawed. But the most common cause is chance, and chance alone. And that's the easiest way of saying it. So if you have proper sampling techniques, and you are confident that the population underlying your null hypothesis is indeed correct, then the most common cause of type 1 and type 2 error is just chance. And that's why we have type 1 and type 2 errors. Okay, so let's put all this information into a nice, easy, handy table. So it goes like this. Remember, we can reach two conclusions with respect to our hypothesis. We can not reject the null hypothesis, or we reject the null hypothesis. Those are the two conclusions we can reach based on our analysis. Now the question always is, how do those conclusions correspond to the real world, to the actual state of the population we're interested in? Now the two conditions of the actual population can be that the null is, quote, true or supported, or the alternative hypothesis is true or supported. And again, I put true in quotes because I don't mean truth as in eternal truth. I just mean supported or upheld. So let's take a look at the case where we do not reject the null hypothesis. So let's say we do not reject the null hypothesis, and the actual condition of the population is that the null hypothesis is true, or it is supported. So our conclusion matches the actual reality. Well, in that case, our sample is correctly inside that non-rejection region, sort of inside that blue part in the graphs we have been using. Now let's say we do not reject the null hypothesis, but the reality is that the alternative is true, or is the real state of the world. Now in that case, we've committed type 2 error. So the sample is inside that non-rejection region due to chance. So that's sort of the second graph we looked at before. Remember, we had all those samples that were well below the hypothesized population mean. But we had that one sample, sample 4, that was actually inside that blue region. And that was our type 2 error. So that's this case. We do not reject the null hypothesis when in fact we should have. Or we get that one sample that's the oddball and it's inside the non-rejection region when the other 95% of them are outside that region. Now look at the conclusion where we reject the null hypothesis down at the bottom. So we reject the null hypothesis, but the actual condition of the population is that the null hypothesis should be supported or is true. So in this case, we have our sample mean outside of the non-rejection region due to some chance. So that was the first graph we looked at. So we had all those means that were sort of in that blue region as we went down. And then we had sample 5 that was outside of that non-rejection region. Now, of course, the other 95% or whatever of those sample means would be inside. So in that case, just by chance, we had a sample outside the non-rejection region Therefore, we rejected the null hypothesis, but we should not have. It was done in error because we had that one oddball sample. And again, that's just the chance. That's just the probability we have to deal with when we are doing statistics. And that's why, again, we have type 1 and type 2 error, and we have to recognize and control for them. Okay, so that wraps up our video on the visualization of type 1 and type 2 errors. And this will really prepare us for the next video where we start actually doing hypothesis testing. But I actually wanted you to see the mechanics of what's going on, how the samples relate to the actual curves. So when we talk about hypothesis testing proper as we go forward, in your mind, you'll actually be able to see the curve. You'll be able to see what's going on, and that helps make it more concrete. Okay? So just a few reminders. If you're watching the video because you're struggling in a class, stay positive and keep your head up. I know you're smart and talented. Everyone else around you does as well, so you should believe so too. Feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way when I upload a video, you know about it. And it's always nice for me to connect with people who watch my videos online. The world is much too big, and life is much too short not to connect with people when we have the chance. If you like the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist, because that does encourage me to keep making them for you. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones for you. And finally, just keep in mind that the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person, or just learn something new in general, that's what really matters. I firmly believe that if you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching. I wish you the best of luck in all your studies and in your work, and I look forward to seeing you again next time when we talk about hypothesis testing.